Hey, Honors Physics, this is Mr. Hausman. We're going to take a look at some of the answers to page 15, 18, and we're going to be looking first at springs. Springs are going to be featured, and that means spring potential energy is going to be featured. And the first example is a trampoline, which many of you have been on, very popular for backyard activities. So a lot of people kind of consider or get kind of confused because, if you were to jump up high or maybe jump onto a trampoline, everyone thinks that the resting position of the trampoline, the unstretched trampoline, is the zero height. But if you look back in some of your notes, the way that it works with potential energy of a spring is that your zero is basically the maximum stretch that a trampoline can do, because that's really the lowest position you can be on the trampoline. Remember, so potential energy due to gravity has to have a zero height, and potential energy of a spring is kind of like that distance that you stretch. So let's take a look through here and let's see if we can solve this one. So what we have to realize is that position A is when the jumper, the trampolinist, is at some significant height above the trampoline. So what kind of energy do you have at the highest point? She starts from rest. So maybe she jumped up in a previous jump, and basically you run out of velocity. So let's assume that at position A, the potential energy due to gravity is the only kind. And then when they fall into the trampoline, to the lowest point, of course it turns into kinetic energy in the process, but then it turns back into, at position B, potential energy of a spring, because there is no height left over. And have you ever noticed that when you're in a trampoline, if you were to do slow motion video, you also momentarily come to rest, so you have no motion. So the formula for potential energy due to gravity at A is mgh. The potential energy at the bottom of the trampoline is 1/2 kx squared. And now we put in the mass. Notice the masses can't cancel out because there's no mass over on B side. G is 9.8. Now here becomes the interesting thing. How high is the jumper relative to the zero height? Well, this is the zero, and according to this, that's an 8-meter drop. It's 7 meters until her body hits the trampoline, but then 1 meter of stretching it. But she still has, right? She still has some potential energy when she's at the surface, right? She has some, but then by the time she gets to the bottom, right, she has zero potential energy due to gravity. A little bit more complicated. And the K value is what we don't know. But as you can see, this trampoline, which is probably made of many, many springs, has a stretch displacement of 1 meter, okay? So your K value comes out to be, and that's not a K of a single spring, it's for the entire trampoline, 6,272 newtons per meter. So that's how we tackle the first one, and we think about the different types of energy. Okay, now this is a bouncing mass in the second one. The mass stops here. It compresses here. Now, the spring itself, if it wasn't bouncing, it's an unstretched string, it drops. It falls, and the spring stretches a certain distance. The mass stops at the lowest point. The spring is stretched 0.5 meters. The mass has fallen through a height of also 0.5 meters. So note X equals H. So let's use conservation of energy to find the K of this spring. So what kind of energy do you have at position A? So what you try to do is you basically know that the total mechanical energy at position A has to be equal to the total mechanical energy at position B if there is no external forces, right? No applied force, no tension force. Gravity is considered a conserved force, so it does not affect the total mechanical energy. Well, at A, right, the spring is basically at rest, right? But it's elevated above its lower position, right? And it falls. So at the very top, it has a form of potential energy. That's its rest position, right? and it's unstretched. This is not compressed. This is basically a relaxed spring, neither stretched nor compressed. But it does have potential energy because it could fall. It could turn into kinetic energy. In fact, it does turn into kinetic energy during the fall, but by the time it hits its bottom, it turns into, right, potential energy that's stored in the stretched spring. Okay, so when it's way up at position A, we know that it has potential energy due to height. It becomes potential energy due to a spring. And now let's plug in 0.1 kilograms times 9.8. Now, what height is it? So we don't care what the height is above the ground. We just need to know what is this height above its lowest point. And according to that, the lowest point it goes is 0.5 meters lower. So its total height is 0.5 meters. We don't know the K value, but we do know that it stretches, right? So that spring stretches out 0.5 meters. Don't forget we have to square that. So let's do some math. 0.1 times 9.8 times 0.5 divided by 1/2 or times 2. And then don't forget to divide by 0.5 squared or 0.25. So I get a K value of 3.92 newtons per meter, right? A much smaller spring compared to the previous one. 16 and I believe it's